So today we're going to talk about optimization. We're looking for maxes and mins in a real life setting. So for once, you're going to see where the derivative has a real life application. So think about in the past when we started finding maximums and minimums. What's the first thing you think of that comes to mind when wanting to find a maximum or a minimum? Derivatives, graphs, we need to be able to find those peaks and valleys. So we're talking about graphing and finding that first derivative, okay? So let's take a look at this function. If we want to find the minimum value of this function, we would take the first derivative. We would set that first derivative equal to 0. We would then go ahead and see, is it a max or min? Now remember, you could do it by a plus-minus chart. If you plugged in 1/2, anything to the left of it would be negative. Anything to the right of that would be positive. So that would be, it would be decreasing then increasing. That tells you that it's decreasing then increasing, that it is a minimum. Okay. You can also do the second derivative test. If you take the second derivative and it's positive, your graph is concave up, so any zeros would be at a minimum. And think it's a parabola, so it has an absolute minimum. It doesn't have a maximum anyway. So if you wanted to find something like the maximum profit, how would you go about doing that? Well, you would have to find an equation that represents the cost of the items, and then you could still use your derivatives to help you. So let's look at the procedure that you're going to go through. There's really 5 main steps for doing these types of problems. First step, read the problem. Okay. Sometimes you want to read it once, do steps 2 through 5, and then read it one more time to make sure you're really doing what they've asked you to do. 2, draw a diagram. This might sound very similar to when we did the related rates or the DREADS problems. You still kind of are following a similar sort of pattern. Next, you want to label the pictures with your variables. You want to find all the equations, including the function that you're trying to minimize or maximize. Usually there's going to be 2 equations that they've given you. One equation will be with the numerical information of the problem, and then one of the equations would be whatever you're trying to maximize or minimize. So say we're trying to maximize area, minimize cost, things of that nature. So we usually have 2 equations minimum that come about in this process. And then you do what you do for any equation when you're finding the absolute max or min using derivatives. So that's kind of the 5-step problem, or 5 steps that you want to take to solve these types of problems. So here's example 1. First, we're going to read the problem. So a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? So you have to think to yourself, we have information about the fencing, and we want to maximize the area. Okay, so when you read that question, you have to think about, okay, usually they're going to give you an information that's a numerical piece of information, like the 2,400 feet of fencing, and then they gave us the fact that we want to maximize the area. So we've read the problem, we kind of have an idea of what's going on. The first thing you want to do next is to draw a diagram. So here's a picture. We've got the river. Here's the river. We don't need fencing along the river. Okay, so we only need fencing 2 X's and 1 Y is all we need when it comes to the perimeter, which we know that fencing total has to equal 2,400. Now, we know that the area of a rectangle is length times width, so I called my length y, my width x, so it's just x times y. Now, just like in related rates, we would only like to have to differentiate with one variable in mind. So let's rearrange our fence information. Let's rearrange that at this time and make it so that we can only use one variable. So if you think about that equation, that's the same as y equals 2,400 minus 2x. So then we can stick that into our area equation. So it would just be x times 2,400 minus 2x is the area equation, which is 2,400x just a second here. Sometimes my eraser goes weird here. 2,400x minus 2x squared. Now that's the equation that we want to maximize. So we find maximums by taking the first derivative. And so if we take the first derivative, we get 2,400 minus 4x. And so we just set that equal to 0. Let's just write that a little different. So 2,400 minus 4x equals 0, when 2,400 equals 4x. So 600. X is 600. Now, is it a maximum? Well, it's our only one. They're usually going to design the problem so that it's going to be a maximum. Otherwise, why would they ask that? But let's just take a moment to remember the ways that we can tell if it really is a maximum. So if we made a chart when x is equal to 600, so we can plug in things like 100 and 700. If we plug 100 into our first derivative equation, which is this equation right here, if we plug 100 in it, we get a positive. If we plug 700 into it, we get a negative. And so think about it. It is increasing then decreasing, so it must be a maximum at 600. Now, it says what are the dimensions of the largest area. So we're not done until we tell you the dimension. So we know that the x direction is 600 feet. And please use units because these are real-life applications. The y dimension is 2,400 minus 2 x's, and x happens to be 600. So y is 1,200, and so the dimensions, it is a 600 by 1,200 foot area. Now, sometimes they'll say, what are the dimensions? Sometimes they'll say, what is the maximum area? Really, it's up to you to answer the question that they've asked. The maximum area would be to multiply that actual out, so 600 times 1,200. If they want the dimensions, they want both the x and the y. So just to be mindful of what the question is that they've actually asked. So example 2, we have a cylindrical can. It's going to be made to hold 1 liter of oil. We're going to find the dimensions that will minimize the cost of the metal to manufacture the can. So this is a real life application that a company would want to make their can so that they use the least amount of material and so that they will not have to use as much metal. It costs them less money. So when you read this problem, remember you're going to get usually one piece of information that is a numerical piece of information, and then one piece of information that is going to be the equation kind of information you want. Now remember, 1 liter is the same as 1,000 milliliters. So usually when doing something like this, we want to go milliliters because milliliter becomes a cubic centimeter and so on. So we can get it to be length. So milliliters can become cubic centimeters, where liter, we don't really do that as much. So that's the same as 1,000 cubic centimeters when it comes to units, just so you kind of are aware of that. So we read it. Now we're going to draw a picture. So we've got this cylindrical can. We know that the can really has two dimensions that we must be concerned about, the radius on the top and the height. Now, let's think about the materials that go into this can. We have the top and the bottom, which is pi r squared. We've got two of those. And then if you think about stretching out the can, think about the top of the can has to wrap around the circle of our can. So that would be 2 pi r, and then it's got to be a height. So the materials of the can have area of 2 pi r squared plus 2 pi r h. Okay. Now, we also know some information about the volume of the can. This is what we're going to try to minimize. We also know the volume of the can is pi r squared h. So the volume, pi r squared h, has to equal 1,000. And again, we want to only have one variable to be concerned about. The easiest variable to solve for in that equation is h. So I know that h is 1,000 divided by pi r squared. And where h is in our equation to minimize, I am going to plug that in so I don't have any h's to worry about in the actual mathematics. So the area is going to be 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Now that I have an equation for the thing I'm trying to minimize, my area, because if you think of area, it's a surface area. It's how much material would it take to make this can. Now I have to take the first derivative. So the first derivative is 4 pi r minus 2,000 r to the negative 2. Now remember what you do to find those critical points for our first derivative. We have to set it equal to 0. So 4 pi r minus 2,000 over r squared. I'm just going to kind of write it so it's a little more visual as to solving an equation. We don't want our r squared to be in the bottom. We wouldn't want our r to equal 0 anyway, because if our r equaled 0, then we would have no cylinder there to speak of. So I'm going to multiply through by r squared, and I'm going to get 4 pi r cubed minus 2,000 equals 0. Now if you think about this equation here, everything is divisible by 4, so let's divide by 4. So we get that pi r cubed equals 500. I'm going to move that 500. 2,000 divided by 4 is 500. I'm going to move that 500 to the other side just because I'm kind of running out of space here. And then if we think about getting the r cubed by itself, r cubed is 500 divided by pi. So the radius has to be the cubed root of 500 over pi. Now, you would never go into a company and said, hey, you want to make your radius the cubed root of 500 divided by pi, because they would look at you like you're crazy. So you would want to give them a decimal equivalent. So our r would end up having to be about 5.4 centimeters. Now that doesn't give us our h. Remember, our h was 1,000 divided by pi r squared. So if you do 1,000 divided by pi r squared, you would get that the height needs to be about 10.9 centimeters. So that would be the dimensions you would want to tell them to make their can. So you'd want the top to have a radius around 5.4 centimeters. You would want the height, and the height, I just used this equation right here. I stuck the r value of 5.4 into that equation, and I found that the height should be approximately 10.9 centimeters. So there's two examples that let you see how a minimum or maximum work. And
I didn't like this one. I thought it was just really ugly.
So in the next example, or the next examples we'll do in part 2 video. So if you want to see more examples, you can just watch it there.